So in the last part of the lecture on recommender systems, we will now see how we can combine latent factor models to also include the global effects that we talked about a few videos ago, right? So the way we want to kind of model both the biases and interactions is in this kind of way, right? In some sense, we would want to model the user bias, we would want to model the movie bias, and then we also want to model the user-movie interaction, right? And the way we can achieve this is very similar to what we already talked about, right? We can have in order to model biases, we need kind of three values. We need the overall mean rating of all the movies in our data set. We need the bias of the user, so how much does the user deviate on the average from the mean rating, and how much does the movie deviate from the mean rating. And then we will be using our latent factors to basically characterize the interaction between users and movies, okay? And the way we can do this is basically we want to put everything together. So this means that we will have an expectation on rating by user X of movie I, even kind of without estimating X's attitude towards the movies that are similar to I. So the idea is that I want to have a rating scale for user X, and I kind of also want to know some kind of popularity of movie I. And I want to have some kind of bias factor for the movie, and I want to also have some factor for the user. So the way we can put everything together is the following. We say that our predicted rating for user X and movie I is the overall mean rating plus the bias for user X plus the bias for movie I plus the user-movie interaction, right? So the way we would reason now about the recommendation, we would say, the mean rating is 3.7, you are a critical viewer, so your BX is -1. You are watching Star Wars, which is a really good movie, that is rated half a star above the average. So now my predicted rating for you based on these biases is 3.2, and then we also include the interaction term to further up or down this rating. Of course, now that we have these biases, we can actually go and compute them using averages as we did before, or we can actually include them as parameters into our optimization problem, right? So for example, we could do the following. We could say, we want to go and find P and Q in such a way that the true rating of an item and the predicted rating of an item differ as little as possible, where what are the things we want to estimate now is we want to estimate B of X, B of I, Q of I, and P of X, right? So now we just kind of added another set of parameters to our models. In some sense, we want to estimate the bias for every user, and we want to also estimate the bias for every movie. So now our regularization term kind of expanded, right? We have the regularization over the matrix factorization part, but then we also have the regularization term over the biases. And the same way as we did before, I can have now this kind of massive beefy equation. I can take the derivative of it with respect to P, with respect to Q, with respect to Bx, and with respect to Bi, and I can do the gradient descent the same way as I did before, and I estimate all these parameters. And of course, as it will turn out, if we do this, performance gets even better. So here is a slide how well these things work. So here I'm comparing, for example, collaborative filtering with the basic latent factors that we talked about in the previous video, and with latent factors that also include biases. And what I'm showing you here is root mean square error, and here is the number of millions of parameters my model has. Okay? And you see that, for example, as I increase the size of the neighborhood in the collaborative filtering, I get from 0.91 all the way down to, let's say, almost like 0.9, while, for example, basically latent factors actually works better than recommender systems. And now if I also learn the biases, basically add biases as parameters that we want to estimate from data, that gives me further improvement, right? And we are almost all the way down to 0.89 root mean square error. One thing to note here is that our model is very complex. Our model has basically 100 million parameters, which is the same as the number of ratings we have, right? So it kind of seems crazy. We have the same number of parameters than we have the data. But because we are using these regularization terms, these penalty terms that we multiply by lambda, even though our model is so complex, it has so many degrees of freedom, the regularization effectively forces the model to be very wise where to kind of use complexity and where to use simplicity. So what we know so far, kind of going back to our chart on performance of various methods, we know that with kind of basic collaborative filtering, we were at 0.94. With a bit more fancy collaborative filtering, we were able to push this down to 0.91. We saw that basic latent factors are at 0.9, and latent factors, including biases, are at 0.98. So kind of using clean methods, this is as close as we can get to the grand prize of 0.8 error 0.85. The question is, how do we go and achieve this final gap? Okay? And lots of work actually went in kind of closing this last final gap before the $1 million prize. So here's the idea. So one thing that we haven't yet used in our model is the idea that ratings change over time. So for example, people analyze the data and noticed that, for example, if we plot time versus the average score of a movie, we see that this in around 2004, the ratings jumped for almost for kind of in a discontinuous way. Another thing we also see is, for example, that the movies age well, in a sense that as the time goes on, the movies get higher and higher ratings. In a sense that older movies get rated higher as the time goes on. So what this means is that we can now take our recommender system and kind of train a separate recommender system for every month, right? So for every separate month of our data set, we will train a separate recommender system so that this way we can also capture the time biases, okay? So what this means is the following. With a simple latent recommender system, including biases, our error was 0.98. By adding also the time factors and the time of day and things like that parameters, we can get down to 0.75. So still away from the grand prize. Notice now that the number of parameters of these models is ridiculous. It's like it's 1 billion parameters, which is huge. It's kind of 10 times more than what we have data. But still, we are kind of disappointed. We are not even close to the prize. So given that we are kind of not even close to the prize, then what do? You kind of get desperate and you try a kitchen sink approach, which basically means you just throw everything together and you hope it will work. So actually the winning solution, what it did is they came up with 130 different recommender systems, and then they basically used when a user movie pair came, they asked each of these 130 recommender systems to rate that pair, and then they blended all these recommendations or these ratings into a single prediction. So in some sense, they took a linear combination of all these ratings, think of it as an average, and then they made a prediction. And using this, they were actually able to achieve this magical 10% improvement. Right? So if you look at the Netflix leaderboard in 2009, the winning team that was from AT&T Research or Bell Labs actually achieved that error, and a few months later, they actually received the check and took this very nice photo. So basically, we saw that using very nice mathematically clean algorithms, we can get very close to the grand prize. But for the last, to make the last few percent, this kind of kitchen sink approach had to be used to make the predictions. But what industry is using today in practice are these latent factor recommender systems using the biases and using gradient descent or stochastic gradient descent to find the parameters of these models. One has to be also very careful with this regularization, otherwise these models tend to very heavily overfit.